Welcome students. Last time you have studied crystal lattice or space lattice and unit cell. Once again I repeat what is the crystal lattice and what is the unit cell. The crystal lattice, it is nothing but the orderly three-dimensional arrangements of atoms in a space. Orderly three-dimensional arrangement of atoms in a space is called crystal lattice. It is diagrammatically representation of constituent particles such as atoms, ions or molecules of the solid. Crystal lattice, it is the diagrammatic representation of constituent particles of the crystal lattice, and that may be either atoms, ions or molecules. Then the unit cell, unit cell, it is the smallest unit of a crystal lattice. It is called as unit cell, or the repeated unit cell forms the crystal lattice. Okay, repeated unit cells forms the crystal lattice. And all crystal lattices, they are bound by a plane surfaces. Okay, crystal lattices are bound by plane surfaces and they are called as planes of the crystal or faces of the crystal. Okay, and when the two planes, they are connected by each other, it is called as edge. Okay, edge of the crystal, and the points or sides of the crystal, here it is equidistant and they forms the planes of the crystals. Okay, the planes of the crystals or faces of the crystal. Okay, and the angle between two planes or two faces, it is called as interfacial angle. Okay, the angle between two faces, it is called as interfacial angle. So up till now you are you have a very well idea regarding what is the crystal lattice or space lattice or simply lattice. Then what is the unit cell, what is the plane of the lattice or face of the lattice, then what is the interfacial angle, and after this we will see the crystallography. And the study of crystal, it is done with the help of three laws. We will see the laws of crystallography. Here the crystals are found in three forms. Okay, crystals are found in three forms. That three forms of crystal are euhedral, subhedral and unhedral. Then the phases, some definitions I repeat here. The phases, here crystals are bounded by smooth plane surfaces. Okay, and that smooth plane surfaces are called as faces of the crystal or plane of the crystal. Okay, then edges. Edges, it is the intersecting line of two adjacent faces is called edge. The intersecting line of two adjacent faces is called edge. Then interfacial angle. The interfacial angle is the angle between two crystal faces as the angle between lines and that are perpendicular to the faces. Such a line are called poles to the crystal face. The interfacial angle is the angle between two normal to two intersecting faces. The interfacial angle between corresponding faces of same mineral will be the same. This is known as the law of constancy of interfacial angle. Here, the crystallography is the branch of science which deals with the study of crystal structure, their development and growth, external form, internal arrangement, and physical properties. Then, the crystallography word derives from the Greek word crystallon, combination of two words, that is cold and congeal, means congealed by cold or cold drop, frozen drop. And at first, the scientist J. Kepler in 1619, it is an astronomer, and Robert Hooke in 1665, inventor of microscope. This gives the concept of crystals as a regular arrangement of spherical particles. Okay, then in 1690, here Christian Huygens studied calcite crystal, a regular internal arrangement of calcite crystal. And in 1669, the scientist Nicholas Stenson studied the law of constancy of angles between the crystal faces. Okay, in 1669, the Nicholas Stenson studied the law of constancy of angles between the crystal faces. Here, some important laws. Here, the first law, it is the law of constancy of interfacial angle. Then the law of rational indices and the law of symmetry. Okay, and the Bravais law. So we see one by one. At first, the law of constancy of interfacial angle. Here, the angles between corresponding faces of the same mineral of the same crystal will be the same. This is known as the law of constancy of interfacial angle. Then the second law, that is the law of rational indices. Here, any crystal face in a space can be represented by three whole numbers. Remember, any crystal face in a space can be represented by three whole numbers if the crystallographic axes are taken as coordinate axis and if intercepts made by the unit cell on crystallographic axis are taken as a unit of arrangement. In short, the law of rational indices, it is nothing but to express the position of plane of that crystal. Okay, to express the position of plane of the crystal. That is the law of rational indices. And the third law, that is Bravais law. A phase is more commonly developed in a crystal if it intersects a larger number of lattice points. This is known as Bravais law. I repeat, Bravais law. A phase is more commonly developed in a crystal if it intersects a larger number of lattice points. This is known as Bravais law. Here, the crystallography, it is studied with the help of three laws. The first law, it is law of constancy of interfacial angle, and it means in the formation of crystal, okay, in the formation of crystal, the angle between two faces, it remains always constant. Then the law of rational indices means we can explain the intercepts made by the plane, okay, with the three coordinate axes, either in whole number or in fraction number. And the Bravais law, that means faces of the crystal are developed and it contains a large number of lattice points. This law is called as Bravais law. Here, see this. This is a interfacial angle. Here, the shape of this crystal, it somewhat changes, though the interfacial angle, it remains same. Here again, the shape it changes, though the angle between two faces, it remains constant. That is the constancy of interfacial angle due to the different pressure temperature condition. The shape of the crystal, it may changes, but the interfacial angle, it remains always constant. This is the law of constancy of interfacial angle, or the interfacial angle, it remains always constant. In the formation of crystal, due to the different conditions, the shape of the crystal, it may changes, but the interfacial angle, it remains constant. Then see the law of rational indices. Here, through the studies of external forms and angular relationship between the crystal faces, some of the fundamental laws have been established which govern the whole crystallography, and they are as follows: the law of constancy of interfacial angle, the law of rational indices, and the law of constancy of symmetry, or simply the law of symmetry. Okay, then here the law of rational indices. The two crystals of the same substance may differ considerably in appearance, that is, in number, size, and shape of the individual faces. In order to describe the external form of crystals, a mathematical method of relating plane to certain imaginary lines in space is used, and that is the law of rational indices. Here, the law of rational indices states that the ratio of intercepts of different faces, the ratio of intercepts of different faces of a crystal with the three axes are constant and can be expressed by rational numbers, that the intercepts of any face of a crystal along the crystallographic axis are either equal to unit intercept, that is, intercepts made by unit cell. In this diagram, this A, B, C, this is a unit cell and it intercepts along x-axis, y-axis as well as along the z-axis. And suppose this distance from, this is origin O to A, suppose it is a small a. This distance from O to B, it is suppose small b, and this distance from O to C, suppose it is small c. That means the intercepts made by unit cell are A, B, C, or some simple whole number multiples of them. And suppose this is another unit cell and it has intercept here NA, then n dash a and n double dash a, etc. are simple whole numbers. In short, the law of rational indices, we can specify the position of plane along the three coordinate axes, either with the help of unit cell or with the help of whole number multiples. Okay, Then see the law of symmetry. Here symmetry is a special characteristic of crystal. Symmetry is a special characteristic of crystal. Crystals are subdivided into 32 classes on the basis of symmetry elements. Remember, crystals are subdivided into 32 classes on the basis of symmetry elements. Two parts of the figure or two bodies, same parts here, are said to be symmetrical when they coincide if they are matched. The transformation or matching of the two symmetrical bodies are called symmetry operation, and the object by which two bodies or figures become symmetrical is called symmetry of element of symmetry. Hence, the symmetry operation is a spatial transformation, rotational symmetry, reflections, and inversion. And for your study, there are three symmetry elements. First one is the plane of symmetry, axis of symmetry, then center of symmetry. And here again the rotation reflection axis. It is not for your study. You have only study the three elements of symmetry here: plane of symmetry, then axis of symmetry, and center of symmetry. This is the symmetric figure of the dog. Then we will see first the plane of symmetry. And plane of symmetry, it is nothing but any imaginary plane that divides the crystal into two equal parts, okay, or two equal halves. A plane of symmetry means any imaginary plane, it divides the crystal into two equal parts. In this diagram, this is a cube, and by this red plane we have divided this cube into two equal parts. So this cube, it has a plane of symmetry. Then here it is again we have another figure, and this is imaginary plane. It cuts this figure into two equal parts. Then this is again we have next figure, and this imaginary plane, it cuts this figure into two equal parts, and it is the plane of symmetry. And any crystal, it may have more than 2-3 imaginary planes. It cuts that crystal into two equal parts. Okay, see here, this is imaginary plane, and it cuts this into two equal parts. Okay, then see here the plane of symmetry. This is also plane of symmetry, rectangular plane of symmetry. Here it is diagonal plane of symmetry. Okay, then the axis of symmetry or rotational symmetry. And the axis of symmetry or rotational symmetry, any shape of crystal, it has a rotational symmetry when it still looks the same after a rotation. Okay, a shape has a rotational symmetry when it will still looks the same after a rotation. Sometimes a figure turns into congruent position when it rotates about an axis. The line about which a figure rotates and turns into congruent position is called axis of symmetry. The angle of rotation by which a figure turns into congruent position is called elementary angle of rotation. The number of turning of congruent position through a complete rotation is called a fold of an axis, and depending on the repetition of the same same position of the crystal, we can have the two-fold axis, three-fold axis, four-fold axis, five-fold axis, and six-fold axis. Okay, then see here the axis of symmetry. Any crystal may have two-fold symmetry axis, three-fold symmetry axis, four-fold symmetry axis, six-fold symmetry axis, and axis of rotatory inversion. And remember, the five-fold symmetry axis and more than six-fold symmetry axis cannot exist in a crystal. See here, this is a cubic structure, cube, and suppose we consider this is the axis of symmetry and we rotate this crystal, and the same appearance of this plane we will have in a one rotation. Okay, so it has one fold axis. Suppose this is a hexagon and this plane we can see after 360 rotation 6 times. So it has 6 fold axis. Okay, 4 fold axis and 3 fold axis also we may have. Then see, these are the axis of symmetry. Then the center of symmetry. Here the center of symmetry, it means in the crystal there is a point, and that point it is in the center of the crystal. Here in this diagram, this point it is in the center. Okay, and the distance of this plane from this point, this plane from this point, and this plane, they are equidistant. The center of symmetry of a cubic crystal. Then this is also center of symmetry. This is also the center of symmetry. Here the center of symmetry. Okay. Then the planes or faces of the cubic structure. See, this is a three coordinate system. X-axis, this one is x-axis, this one is y-axis, and here it is z-axis. And this one plane here, it cuts x-axis at this point, okay, and it remains parallel to the y-axis and z-axis. Here the intercept of this plane on the x-axis only. So this plane is called as 1 0 0 plane, and 1 0 0 means it intercepts at a one axis and remains parallel to the two axes. Here intercept are on the x-axis. Suppose it is a unit cube. On x-axis it is at distance 1, y-axis infinite, on z-axis it is also infinite. So such a plane of the cube, it is called as 1 0 0 plane. 1 0 0 plane. Then see, this is another plane and it cuts x-axis as well as y-axis, x-axis and y-axis, and remains parallel to the z-axis. Such a plane it's called as 1 1 0 plane. Okay, as in the first figure you have seen the 1 0 0 plane, that means that plane or that face, it cuts at a one coordinate axis. This has intercept on two coordinate axes. This plane is called as 1, 1, 0, and this plane, see, this plane, it cuts all the three coordinate axes, and such plane is called as 1, 1, 0 plane. These are the planes of the cubic system. Okay, planes of the cubic system. This is the 1, 0, 0 plane. This is the 1, 1, 0 plane, and here it is the 1, 1, 1 plane. See here, this is the 1, 1 plane, 1, 0, 0 plane, and if we have this here, this is here, and this becomes a 1, 1, 0 plane, and if we join this point here and here, we have a 1, 1, 1 plane. Okay, then see, 1, 1, 0 plane, here it is 1, 1, 1, 1, 1 plane, this one, and here it is 1, 0, 0 plane. Okay, see the next diagram of 1, 0, 0 planes. Here 1, 1 plane, and these are the 1, 1, 1 planes. For your study, there are only 3 planes: 1, 0, 0, 1, 1, 0, and 1, 1, 1 plane. Okay. So next time you will study the Miller indices and West indices for to specify the different planes of the crystal.